beneath the skin of the tropical sea, where the sun filters into fractured shards of turquoise light and the reef seems to hum with life, an assassin waits in silence.
It is not a shark, nor a moray eel. It is not the looming shadow of a barracuda.
Instead, the most violent predator in this coral kingdom is no larger than the length of a human hand. The mantis shrimp, tucked neatly inside its burrow, is poised like a living weapon. Its colors shimmer like liquid fire, iridescent greens, crimson streaks, bands of sapphire across its armored carapace. At first glance, it seems almost ornamental, too radiant to be feared. But in truth, this crustacean is the reef's equivalent of a loaded gun. To understand its power, one must look at the arms folded neatly against its chest. These are not claws in the usual sense, not pincers built for gripping or tearing. Instead, the mantis shrimp wields dactyl clubs, a pair of spring-loaded hammers that embody one of evolution's most radical designs. Each strike begins with a mechanism hidden deep inside the limb, a saddle-shaped structure of rigid chitin that stores elastic energy like a compressed bow. When the latch releases, the arm snaps forward with terrifying speed. In a blink, the club accelerates at 20 to 30 meters per second, faster than most bullets leave a handgun barrel. For the unlucky snail, crab, or small fish caught in range, the result is absolute obliteration. Shells shatter, scales scatter, and prey is reduced to fragments before it realizes danger was even present. But the violence does not stop at the club's surface. With every blow, the mantis shrimp births something that exists in both the mechanical and physical extremes of our universe: cavitation bubbles. The sheer speed of the strike forces water pressure around the club to plummet. In that fleeting pocket of low pressure, a vapor bubble blooms, expanding like a ghostly sphere. A heartbeat later, the bubble implodes, collapsing under the crushing force of the surrounding seawater. The implosion releases a shockwave powerful enough to finish off prey, even if the club itself missed its mark. And in that collapse, for a fraction of a second, conditions reach a scale that defies imagination. Temperatures spike to those measured on the surface of the sun, and in the chaos, a tiny flash of light bursts forth. This phenomenon, known as sonoluminescence, makes the mantis shrimp one of the only animals capable of producing light, not from a chemical reaction, but from physics itself. To the human eye, the flash is invisible. It happens too quickly, at too small a scale. But within the reef, the echo of this violence is unmistakable. The very architecture of the mantis shrimp's clubs is as extraordinary as the force they deliver. Unlike brittle materials that would crack under repeated stress, these hammers are built on a microengineering blueprint, refined through millions of years of evolution. The core of the club is formed from a spiral arrangement of chitin fibers known as a helicoid structure. Imagine a stack of plywood, but twisted into a spiral staircase at the microscopic level. This geometry distributes the force of impact across layers, preventing cracks from spreading and fractures from accumulating. Over time, even after thousands of strikes against rock-hard shells or aquarium glass, the club remains functional. Human engineers, fascinated by this natural design, have studied it for applications in military armor and aerospace materials, recognizing that nature has already solved problems of resilience that still challenge modern technology. But the mantis shrimp story is not only one of brute force, it is also one of vision unlike any other on Earth. Where most creatures see in three basic colors, mantis shrimp possess eyes divided into compound units, each with rows of receptors tuned to an astonishing spectrum. They can detect ultraviolet light invisible to us, perceive polarized light patterns that no mammal can sense, and interpret circular polarization, a phenomenon few animals exploit. With this sensory arsenal, mantis shrimp do not just see more colors, they see a hidden code layered across the reef. The glint of fish scales, the sheen of polarized reflections off an exoskeleton, or the subtle shimmer of a rival's body become signals in a secret language of light. For a predator that relies on ambushes launched in milliseconds, this ability to decode visual patterns is not decoration, it is survival. By spotting faint contrasts and hidden cues, the mantis shrimp anticipates movement, locates prey, and avoids larger predators in ways that seem supernatural to us. From inside its burrow, the shrimp tests its world with cautious peeks. Its stalked eyes move independently, scanning like periscopes across a kaleidoscope of coral, sand, and darting fish. A passing goby is dismissed. It is too quick, too wary. A hermit crab inches too close, oblivious to the danger, and the shrimp stiffens. The strike comes so suddenly that sound lags behind action. First the club launches, then the prey crumples. Then, just a beat later, the reef vibrates with the muffled crack of impact. In many reef habitats, these hits accumulate into a chorus. Divers who have drifted quietly across shallow corals often describe the reef as alive with snapping, a soundscape dominated not only by pistol shrimp, but also by the hammering of mantis shrimp. This acoustic presence is more than background noise. It marks territories, intimidates rivals, and shapes the rhythm of reef life in subtle, far-reaching ways. What makes the mantis shrimp's power even more striking is its scale. This is not a giant predator like a shark or an octopus. Its reach is measured in inches, its body weighs only a few grams. And yet, it generates forces that rival our most advanced weapons. The cavitation bubbles it unleashes do not just kill, they create microenvironments of extreme physics. The heat of collapsing bubbles, though lasting only nanoseconds, is so intense that it could boil water locally. The shockwaves radiate outward, stunning or even killing prey that survives the initial strike. Scientists have likened this combination of mechanical and physical attack to a two-punch strike. First the hammer blow, then the collapsing bubble's detonation. Prey struck by both has virtually no chance of escape. The ecological role of the mantis shrimp extends beyond hunting. By breaking open the shells of snails and crabs, they influence the recycling of calcium carbonate in the reef. By occupying burrows and repelling rivals with their thunderous strikes, they carve micro-territories in crowded ecosystems where every crevice is contested. And by existing as both predator and prey, they themselves are hunted by groupers, moray eels, and larger fish. They weave into the food web in ways that ripple outward. Remove them, and the structure of the reef changes. Their absence would mean fewer shell fragments, altered competition, and shifts in prey populations. If the mantis shrimp has a flaw, it is its own ferocity. In captivity, they are infamous for shattering aquarium glass, a testament to both their power and their restless aggression. For this reason, aquarists dub them thumb splitters, a warning earned by painful encounters with those who underestimated them. But in the wild, this aggression is tempered by ecological purpose. Their strikes may be weapons, but they are also instruments of balance, ensuring that prey populations remain checked and that the reef's endless competition maintains equilibrium. And so, within this underwater arena, the mantis shrimp remains one of the strangest contradictions in biology. A creature of jewel-like beauty that behaves like a living warhead. A palm-sized animal capable of unleashing temperatures that mimic stars. A predator that sees light in ways alien to human perception. If the reef is a symphony of survival, then the mantis shrimp is its percussion section. A relentless beat of hammer strikes and collapsing bubbles, sounding out the tempo of violence beneath the waves. The next time one drifts over a coral garden and hears a faint popping, it is worth remembering. Somewhere in the crevices below, a mantis shrimp has just unleashed a blow that reshaped the physics of water itself. The reef is listening. The prey is silenced. And the shockwaves ripple outward, invisible yet undeniable, proof that sometimes the smallest creatures carry the loudest weapons. The water seems still in the early morning. Mangrove roots lean like crooked fingers into the tide, their shadows etched across the shallows, their tangling shapes mirrored on a glass-smooth surface. Beneath this calm, the water itself is wired with danger, though the threat is nearly invisible. Drifting just beneath the surface, as pale and transparent as a ghost, the box jellyfish waits. To the untrained eye, it seems like nothing more than a wrinkle in the current, a shimmer of refracted light. Yet hidden within that crystalline body lies a weapon so fast and so devastating that it has been called one of the most efficient killing systems on Earth. The box jellyfish does not strike with teeth or claws. Its weapon is far more insidious, woven into the architecture of its trailing tentacles, which hang like curtains of death. Each tentacle bristles with thousands of microscopic cells known as cnidocytes, tiny capsules primed like spring-loaded syringes. Inside each capsule coils a thread armed with venom held under explosive pressure. The trigger for this system is a delicate hair-like projection called a cnidocyl. When brushed by the barest touch of skin, the hair flips, releasing the trap in a microsecond. The thread unfurls with the speed of a harpoon, puncturing flesh and injecting venom in an instant. To put that speed in perspective, the firing of a cnidocyte is one of the fastest cellular processes known to biology. It is faster than a human nerve impulse, faster even than the blink of an eye. In less than a millionth of a second, the capsule has fired, the thread has penetrated, and the venom has begun to diffuse. Multiply this by the thousands of nematocysts along a single tentacle, and the effect becomes catastrophic for small fish and catastrophic for an unlucky human who brushes against the jelly's curtain of threads. The venom, a complex cocktail of proteins and peptides, targets heart muscle and nervous tissue, triggering extreme pain, paralysis, and in severe cases, cardiac arrest. To call it potent is an understatement. Box jellyfish venom is among the most powerful toxins produced by any animal. Yet, for all their lethality, box jellyfish are not mindless drifters in the way most of us imagine jellyfish to be. Suspended within their cube-shaped bells are structures known as rhopalia, sensory clusters that house a surprising array of organs. Each rhopalium carries up to 6 eyes, arranged into different types. Some are simple pits sensitive only to light and shadow, while others are more sophisticated lens-bearing eyes capable of forming images. Taken together, a single jellyfish may carry as many as 24 eyes. This arrangement allows box jellies to detect obstacles, orient themselves to the surface, and navigate the maze of mangrove channels where they hunt. It is an unsettling thought, an animal without a brain, whose body is 95% water, possessing not only eyes, but also enough neural wiring to coordinate vision with movement. They do not think in the way we do, but they sense the world with purpose. They can swim actively, pulsing their bells to maintain position, avoiding roots and pilings, turning deliberately toward open channels. Their eyes, set in 4 rhopalia spaced evenly around the bell, grant them a kind of 4-directional awareness. The sea, in their perception, is not an aimless drift, but a world of shapes, shadows, and vertical markers. In these shaded channels, the jellyfish's tactics take on the geometry of a minefield. Tentacles may trail for meters, nearly invisible in the shifting water. They spread in broad curtain-like arrays, forming barriers through which small fish must pass. Currents amplify the trap, drawing prey into the stinging threads as they swim with the tide. Unlike active predators that chase and pursue, the box jellyfish wins by invisibility and positioning. Its body is clear, refracting little light, making it nearly impossible to detect in shallow waters. To a fish, the mangrove root maze is already a dangerous obstacle course. When the jellyfish weaves its tentacle curtain across these narrow spaces, escape routes collapse. What was once a safe corridor becomes a gauntlet, where any brush with an invisible filament is fatal. The venom acts with brutal efficiency on fish. A brush of tentacle paralyzes muscles almost immediately, ensuring prey cannot dart away into the safety of the roots. Immobilized, the fish drifts into the jelly's tentacles, where more nematocysts fire, delivering additional doses until resistance ends. From there, the tentacle's cilia transport the prey slowly upward to the bell, where digestion begins in a simple gastric cavity. It is not elegant, but it is devastatingly effective. What makes this system more remarkable is its precision in context. In murky mangrove waters, where visibility is poor and prey can vanish into roots within seconds, a predator must kill almost instantly or risk losing its meal. Speed is not just advantageous, it is essential. The box jellyfish's venom has therefore evolved not only to kill, but to kill faster than almost anything else in the sea. In this evolutionary arms race, the jellyfish has tipped the scales of survival through chemistry and physics, rather than muscle and bone. For humans, encounters with box jellyfish are less about predation and more about accident. Swimmers in northern Australia or Southeast Asia sometimes stray into jellyfish-rich waters during breeding season, when they gather in shallow coastal zones. The result can be catastrophic: searing pain, blistering welts, and in severe cases, collapse within minutes. Despite their fearsome reputation, fatalities remain relatively rare, but the threat is real enough to inspire beaches to erect jellyfish nets, lifeguards to carry vinegar sprays, and medical researchers to pursue antivenoms. Here, myth and fact often collide. Vinegar, for instance, is commonly recommended as first aid, not because it neutralizes the venom, but because it deactivates unfired nematocysts clinging to the skin. Rubbing the sting, on the other hand, worsens matters by triggering more stingers. Freshwater rinses are equally dangerous. They cause nematocysts to discharge en masse. The most effective treatments combine immediate vinegar application with careful removal of tentacles, followed by medical support to manage the systemic effects of venom. In recent years, advances in antivenom and cardiopulmonary intervention have reduced deaths, but the danger remains woven into local cultures. Children in Queensland are taught jellyfish safety as instinctively as road safety. Beyond the human dimension lies a broader ecological story. Box jellyfish, despite their threat to swimmers, are not villains in the marine system. They occupy a role as mid-level predators, helping regulate small fish populations that thrive in nutrient-rich coastal waters. Their presence in mangrove channels hints at ecological interdependence, for these waters teem with larvae, plankton, and juvenile fish seeking shelter. As climate change alters sea temperatures and coastal ecosystems, the distribution of box jellyfish is shifting. Warmer seas allow them to extend their range, and changes to mangrove and seagrass habitats may amplify encounters with humans. Conservationists therefore walk a tightrope between protecting public safety and recognizing that these gelatinous hunters are themselves indicators of ecological health and imbalance. The box jellyfish is a paradox, a creature both fragile and lethal, drifting yet purposeful, brainless yet possessed of vision. In the light of a dive torch, its cube-shaped bell glows like glass, its tentacles nearly invisible threads of electricity suspended in water. One careless brush against those threads and the illusion of fragility evaporates, replaced by agony and awe at the hidden power of evolution. In the grand theater of the reef, the mantis shrimp announces its presence with thunder, but the box jellyfish is silence embodied. It does not hammer or chase. It waits, invisible, stringing the water with weapons that fire faster than thought, weapons that turn the sea itself into a lattice of lightning strikes. For the fish that swim these mangrove channels, the water is alive with ghosts. For us, it is a reminder that the ocean is not only a cradle of beauty, but also a crucible of power, transparent, silent, and waiting just beneath the surface. The ocean floor looks deceptively quiet. Scattered rubble, threads of seagrass swaying with the tide, and patches of coral rubble blend into a muted canvas of browns and greys. Then, without warning, the seabed shivers. A rock seems to move, an algae tuft ripples with unnatural intent, and suddenly what looked like nothing at all becomes a cuttlefish. No splash, no sudden charge, sudden. One moment the animal is invisible, the next it is present, an editor of its own body, a master illusionist capable of rewriting its skin like a live performance. Cuttlefish belong to the cephalopod order, kin to squids and octopuses, but their evolutionary theatre is unique. Where the octopus manipulates its environment with arms and the squid thrives in open water speed, the cuttlefish has perfected the art of real-time self-transformation. Every square centimeter of its body is alive with potential, a shifting mosaic of cells and structures that can create color, pattern, brightness, even texture on demand. For predators and prey alike, this is a living paradox, an animal that exists everywhere and nowhere, a body that doubles as both shield and signal. The core of this ability lies in 3 layers of specialized skin cells, each tuned to a different dimension of light. At the surface are chromatophores, tiny sacs of pigment, yellows, reds, browns, each controlled by a ring of muscles. When contracted, the pigment sac expands, like an umbrella unfurling, revealing rich patches of color. Beneath them lie iridophores, plates that reflect light through structural interference, creating shimmering blues and greens, not from pigment, but from physics. At the deepest level are leucophores, broad-spectrum reflectors that scatter ambient light, providing a pale base that can amplify or mute colors above. Together, these layers form a living screen with millions of pixels, each pixel no larger than a pinhead, but capable of dramatic shifts. Unlike human screens, which refresh in milliseconds, the cuttlefish's display is constantly refreshed by neurons firing directly into each cell. The animal's nervous system is wired for art, with its brain devoting significant architecture to controlling this skin orchestra. Yet color is only the beginning. Cuttlefish skin can sculpt itself into three-dimensional illusions. Tiny bundles of muscles manipulate papillae, fleshy protrusions that can raise and collapse like miniature tents. When extended, they transform a smooth body into a textured mimic, algae-like fronds, spiky rubble, or rough coral ridges. Combined with color change, this texturing creates depth that deceives not just the eye, but the tactile senses of predators probing with touch. A cuttlefish pressed against a rock can become rock itself, its outline broken, its texture indistinguishable from its backdrop. To divers, the effect is uncanny. One can stare directly at the animal and fail to recognize it until it moves. But the cuttlefish's genius is not just in hiding. It also communicates through channels invisible to most of its predators. Among its repertoire lies the use of polarized light, a property of reflected waves that align in specific orientations. While humans cannot naturally see polarization, many marine animals, including cuttlefish, can. By adjusting the reflective structures in their skin, cuttlefish produce polarized patterns, hidden messages visible only to those tuned to the same spectrum. In courtship, a male may flash polarized signals to a female while remaining apparently drab to surrounding fish. To a passing snapper or barracuda, the cuttlefish appears as a patch of sand. To its intended partner, the skin glows with a private language of stripes and pulses. This dual channel of communication, camouflage for predators, signals for mates, is one of nature's most ingenious compromises. For prey capture, cuttlefish deploy illusions so surreal they border on optical tricks familiar to stage magicians. One is the passing cloud display, where waves of dark and light ripple across the skin, mimicking the shadow of a cloud drifting overhead. To a small crab or fish, the moving bands mesmerize, disrupting normal escape responses. Another is the zebra strobe, rapid pulses of alternating stripes that appear to freeze prey in place. While the exact neurological mechanisms in the prey are still under study, evidence suggests these displays overload the visual processing circuits of fish, leaving them momentarily paralyzed. In that frozen instant, the cuttlefish lunges, shooting out its tentacular arms with pinpoint precision. The attack is lightning fast, but it is the illusion that makes the kill possible. These tactics reflect a deeper cognitive complexity. Cuttlefish are not mere skin robots programmed by instinct. Laboratory studies reveal their capacity for problem-solving, memory, and even strategic trade-offs. When faced with predators that rely on vision, they prioritize camouflage. When confronted by predators that hunt through chemical cues, they may flee instead, recognizing the futility of disguise. They have demonstrated the ability to delay gratification, choosing a more rewarding meal later over a smaller one now, an ability often associated with mammals and birds. In the wild, this translates into subtle decisions about when to remain hidden and when to break cover for a strike. Camouflage, after all, is not permanent. The more time a cuttlefish spends matching its background, the less time it spends hunting or mating. Each moment of disguise carries a cost, and the animal balances these costs against the urgency of hunger, the presence of rivals, or the movement of currents. This cognitive twist is visible in the way cuttlefish edit themselves in real time.
Imagine the scene. A juvenile hovers above seagrass. A shadow passes. A barracuda cruising overhead.
Instantly, the cuttlefish flattens its body, papillae rising into grass-like fronds, chromatophores shifting into mottled greens and browns. The predator drifts by, fooled. Seconds later, a shrimp scuttles across the sand. In a flash, the skin turns into a pulsing strobe, Papillae collapse to streamline the body, and tentacles fire outward. From prey to predator, from invisible to dazzling, the cuttlefish edits its role with the precision of a film director cutting between scenes. The continuity is seamless because the animal's body is both actor and stage. Beyond predation, these transformations ripple through the ecosystem in subtle ways. By preying on shrimp, crabs, and small fish, cuttlefish regulate populations that might otherwise overgraze algae or overpopulate reef crevices. Their camouflage allows them to survive long enough to reproduce in coastal shallows, where their eggs, encased in ink-stained capsules, provide food for other species. Their very bodies, filled with calcium carbonate from their cuttlebone, contribute to nutrient cycles when they die, returning minerals to the sea floor. Thus, their skin artistry is not mere spectacle. It is an anchor point in the dynamics of reef life. Human fascination with cuttlefish reflects our deeper curiosity about intelligence beyond vertebrates. How can a creature with such a short lifespan, often no more than 2 years, pack so much cognitive complexity into such a brief existence? How can an animal without bones orchestrate such intricate body displays? These questions reveal the cuttlefish as both scientific puzzle and evolutionary marvel. Engineers study its skin to inspire new display technologies, from adaptive camouflage clothing to dynamic architectural surfaces. Neuroscientists probe its brain to understand distributed control systems, where millions of independent skin cells respond in synchrony to centralized commands. Each discovery underscores how little we truly know about the boundaries of intelligence in the animal kingdom. In the end, the cuttlefish remains a living contradiction. It is a creature of concealment, yet one of the ocean's most flamboyant artists. It thrives on deception, yet reveals truths about evolution's creativity. On the seabed, its camouflage may make it vanish from sight, but as an evolutionary story, it is impossible to ignore. Its skin is not simply a covering, it is a canvas, a screen, a language, and a weapon. It is an instrument tuned to survival, playing in a theater where the audience is predator, prey, and mate all at once. To swim above a cuttlefish is to witness editing in real time, the sea itself being rewritten frame by frame. A patch of sand shimmers into stripes, a rock ripples into zebra strobe, a shadow shifts into passing cloud, and somewhere in those illusions, a shrimp disappears, a predator is fooled, and the balance of the reef tips ever so slightly. The cuttlefish leaves no signature but the silence of disguise. For those who glimpse its artistry, however brief, it is clear that evolution has written one of its most brilliant scripts into the living skin of this underwater editor. On a twilight reef, where light has thinned into cobalt shadows and fish schools gather for the night, a ripple of motion disturbs the seabed. A rock shifts, a patch of algae seems to stir, and then, in a burst of uncanny liquidity, the octopus reveals itself. It is not a predator that arrives with thunder, like the mantis shrimp, nor one that waits with invisible threads, like the box jellyfish. The octopus's weapon is far stranger, a body that is both everywhere and nowhere, guided by a mind that does not live solely in its head. Unlike most animals, the octopus does not keep its brain confined to a single command center. Instead, its intelligence is distributed, woven throughout its body. 2/3 of its neurons reside not in the central brain, but in its arms. Each arm functions as a semi-independent unit, capable of tasting, touching, and making local decisions without waiting for instructions from above. An arm can probe a crevice, manipulate a shell, or even wrestle with prey while the central brain orchestrates broader strategy. It is as if the animal were a coalition of 8 separate minds, linked by a higher conductor that sets the overall rhythm but does not micromanage the details. This architecture confers a flexibility rare in the animal kingdom. When an octopus explores, its arms fan outward like scouts, each sampling textures, gradients, and scents. A single arm may pause to investigate a crack, curling with delicate precision, while another is already testing the grip of a rock. The central brain does not issue every command. Instead, it trusts the local intelligence embedded in each limb. In essence, the octopus can think in parallel, processing multiple sensory streams simultaneously, something no mammal can truly achieve. This distributed brain allows it to solve problems in real time, adapt to changing circumstances, and respond with an agility that feels almost alien. But intelligence alone is not survival. The octopus's most astonishing adaptation may be its ability to disappear at will. With a skin as dynamic as the cuttlefish's but controlled with even greater nuance, the octopus can vanish against sand, rock, or coral in less than a second. The process is not random mimicry but contextual camouflage. Specialized skin cells known as chromatophores expand or contract to match background colors. Beneath them, iridophores scatter structural iridescence, while leucophores reflect ambient light. Together, these layers allow the octopus not only to blend with a flat surface, but also to capture the visual texture of its surroundings. More remarkable still is its ability to manipulate edges and spatial frequencies. Camouflage in the reef is not simply about copying color. Predators' eyes are tuned to detect outlines, shadows, and contrasts. The octopus knows this instinctively. By raising papillae into ridges, bumps, or fronds, it breaks its own silhouette, fragmenting its shape into something unrecognizable. A smooth octopus pressed against coral rubble suddenly sprouts algae-like tufts. A pale octopus on sand ripples into a faint, shifting mirage of grains. The illusion is not static. It constantly updates as the octopus samples visual cues with its extraordinary eyes, which can adjust to contrasts beyond human perception. In scientific terms, the octopus is matching spatial frequencies, editing its body not to be invisible to us, but to be invisible to the specific sensory biases of its predators. Camouflage may keep it hidden, but the octopus also engineers its own fortresses. Many species construct dens, carefully selecting and arranging objects to fortify the entrance. A coconut half becomes a door. A pair of clamshells form barricades. Stones are placed strategically, rolled into position with patient determination until the entrance becomes a locked vault. Divers often find middens outside these dens, piles of discarded shells from past meals that double as warnings and architectural reinforcement. Some octopuses even carry portable shelters, coconut shells clutched like shields, to be deployed as gauntlets when retreat is impossible. These behaviors reveal not just tool use but foresight, an ability to plan for scenarios beyond the immediate moment. Hunting strategies reveal the same ingenuity. An octopus may trap crabs by sealing burrow entrances with rocks, effectively laying a prison around its prey. Others use their arms as nets, spreading them wide to cover an area while jetting forward, flushing shrimp or fish directly into their grasp. Each capture is followed by a quick injection of venomous saliva that paralyzes prey, allowing the octopus to consume it at leisure. Its arms, lined with hundreds of suckers, provide a tactile map of its world, each sucker capable of independent grip and chemical sampling. To an octopus, taste and touch are fused. Every surface is information. When camouflage and traps fail, the octopus relies on performance. Confronted by a predator, it can shift into diamatic displays, sudden dramatic transformations meant to startle or intimidate. Skin flushes into bold patterns, eye spots flare across its body, and arms splay wide, making the animal appear larger than life. If this fails to buy escape, it unleashes ink, but not as a simple smokescreen. The ink, mixed with mucus, forms pseudomorphs, ghostly shapes that resemble the octopus itself. These decoys drift in the water, drawing predators' strikes, while the real animal jets away under propulsion. The jet is powered by a muscular siphon, which can expel water with explosive force, sending the octopus rocketing backward faster than most fish can pursue. In moments of absolute desperation, an octopus may even sacrifice an arm, allowing it to thrash independently while the body slips into safety. That lost limb will regrow in time. Yet for all their brilliance, octopuses live under a cruel bargain. Intelligence, camouflage, tool use, these are gifts of evolution, but they come at the cost of time. Most octopuses live scarcely longer than a year or two. Even the largest species, the giant Pacific octopus, rarely exceeds 5 years. Their lives are compressed into an intense sprint: rapid growth, ingenious survival, explosive reproduction, and sudden decline. Females, after laying thousands of eggs, devote themselves entirely to guarding and aerating their brood, refusing food until their bodies waste away. Males often die shortly after mating, their genetic purpose complete. Why such brilliance should burn so briefly remains an evolutionary puzzle. Part of the answer lies in their lineage. As invertebrates, octopuses lack the long lifespans conferred by protective skeletons or slow metabolism. Their strategy is to live fast, reproduce in abundance, and rely on intelligence to survive the interim. But it is also a stark reminder that intelligence alone does not guarantee longevity. The reef's geniuses are also its ephemeral players, flashes of brilliance that vanish almost as quickly as they appear. Still, in those short lives, the octopus rewrites what it means to be an animal. It proves that a brain need not be centralized to achieve sophistication. It shows that camouflage can be more than hiding. It can be art, deception, even theater. It demonstrates that tools and foresight are not the sole province of primates or crows, but can emerge in a boneless liquid body. Perhaps most poignantly, it reminds us that evolution can produce brilliance not for permanence, but for intensity, a brief flare of genius in a hostile sea. To watch an octopus is to witness a paradox. It is at once a rock and a cloud, a predator and a phantom, a mind that thinks with 8 arms yet fades in only a few years. In the darkness of the reef, when a stone ripples into life and vanishes again into the sand, one understands. The octopus is not only a creature of the sea, but also a metaphor for the fleeting brilliance of adaptation. It is intelligence embodied in liquid form, ephemeral yet unforgettable. The ocean at dawn is alive with murmurs. Schools of baitfish shimmer in tight formation, twisting into liquid mosaics as they try to disappear into one another. The water is filled with faint crackles of shrimp, distant rumbles of ships, and the low thrum of currents moving across the seabed. Cutting through this cluttered soundscape comes another signal, an ordered rhythm of clicks, each one sharp, precise, and deliberate. Somewhere beyond the veil of visibility, a dolphin is sculpting the ocean, not with its body, but with sound. Echolocation is the dolphin's defining gift, a sensory system that transforms the opaque sea into a world of clarity. Unlike humans who rely heavily on light, dolphins operate in a medium where visibility often collapses within a few meters. Instead, they generate sound pulses, short, high-frequency clicks produced in nasal sacs just below the blowhole. These clicks are channeled forward through the melon, a fatty organ in the forehead that acts like an acoustic lens, focusing the sound into a narrow beam. When the clicks strike objects, they bounce back as echoes, which the dolphin receives through its jawbone and inner ear. The returning echoes are processed in the brain not as abstract vibrations but as vivid, three-dimensional imagery. To a dolphin, a fish hidden in murky water is not invisible. Its shape, size, even density become immediately clear through the silent language of echoes. This is not passive hearing but active imaging, a sonar system rivaling military technology. Dolphins can adjust the frequency and interval of their clicks to match context. Slow, scanning clicks for long-distance detection, rapid buzzes for close pursuit. In effect, they zoom in on their quarry, resolving fine detail as a camera lens might shift from wide-angle to macro focus. Some studies suggest dolphins may even perceive internal structures, detecting gas-filled swim bladders or distinguishing between metal and plastic objects. It is a reminder that the sea is not silent for them, but a tapestry of shapes woven entirely in sound. But dolphins are not content to sense the ocean, they manipulate it. In shallow waters, groups of bottlenose dolphins perform an engineering feat that few predators on Earth can match: bubble netting. One or two individuals swim in circles around a school of fish, releasing steady streams of bubbles from their blowholes. The bubbles rise and form a shimmering ring, a wall of silver spheres that fish instinctively avoid. Trapped inside this corral, the school tightens, compressing into a dense mass. Then, at a signal, the dolphins charge through the center, mouths agape, gorging on prey that has nowhere to run. The geometry is striking. Predators reshaping the physical properties of water to herd prey as efficiently as a shepherd fences sheep. In other regions, dolphins employ variations of this tactic. Along muddy coasts, Some drive fish into shallows by beating the seafloor with their tails, raising plumes of sediment that form a visual and tactile barrier. The fish, disoriented and unwilling to enter the turbid cloud, leap clear of the water, only to land directly into the dolphins' waiting mouths. In deeper waters, coordinated groups create pressure bars by swimming tightly together, forcing prey into a vertical wall. Each of these methods relies not only on individual ingenuity, but also on coordination, trust, and an understanding of fluid dynamics. The dolphins, in essence, are engineers of the sea, using sound, bubbles, and mud to sculpt the battlefield of predation. This inventiveness extends beyond hunting. Dolphins have repeatedly demonstrated tool use, a rare trait in the marine world. In Shark Bay, Australia, researchers have documented a behavior known as sponging, where dolphins break pieces of marine sponge and wear them on their snouts like gloves. These sponge masks protect their skin as they probe sandy bottoms for buried fish, allowing them to exploit resources unavailable to bare-faced peers. What is most telling is how this behavior spreads. Sponging is not instinctive. It is passed from mother to offspring, generation after generation. This makes it cultural, a learned tradition embedded in dolphin society. Some lineages specialize in sponging, while others develop different foraging strategies. For an animal often regarded as playful, this persistence of transmitted knowledge reveals a society bound not only by genes, but by shared innovations. And play for dolphins is never trivial. Wave surfing, bow riding, and even the harassment of other animals serve deeper functions than entertainment. When dolphins surf the wakes of boats or the rolling swells near shore, they are practicing maneuverability, building muscles, and learning the dynamics of fluid motion in ways that pay off during high-speed hunts. When they chase seabirds or toss fish into the air, they are refining strike precision, experimenting with prey handling, and strengthening social bonds. Even harassment of sharks or turtles, while seemingly wasteful, can be understood as training scenarios, group rehearsals of strategy, testing how individuals coordinate to corner or distract larger creatures. To a dolphin pod, play is rehearsal disguised as joy, a schoolroom without walls where the lessons are written in waves and breath. This intricate reliance on sound and bubbles makes dolphins especially vulnerable to one of humanity's least visible impacts, noise pollution. For tens of millions of years, the ocean's soundscape has been dominated by natural rhythms, the crackling of reefs, the calls of whales, the crashes of waves. In recent centuries, shipping lanes, sonar pulses, and industrial activity have reshaped that soundscape into a cacophony of engines and propellers. For dolphins, whose biosonar depends on clarity, this is not just a nuisance but a direct threat. Constant background noise masks echoes, blurs signals, and forces dolphins to work harder to perceive their world. In areas of intense traffic, dolphins alter their click frequencies, increase their call volume, or abandon habitats entirely. What to us is a low hum of commerce is to them a wall of interference that erodes their most vital sense. The tension between dolphins and human noise underscores the fragility of even the most adaptable predators. Their ingenuity, bubble nets, echolocation, tool use, depends on a medium that must remain transparent to sound. Cloud it with industrial clamor, and their edge dulls. Conservation in this case is not about protecting dolphins from predators, but from a sensory blindness we have imposed on them. Efforts to establish quiet sanctuaries, regulate sonar use, and alter shipping routes are not luxuries. They are necessities for maintaining one of evolution's most remarkable achievements. To witness dolphins in their element is to glimpse intelligence translated into physics. Imagine a pod driving fish into a bubble corral, each individual in perfect synchrony, the sea itself reshaped into a trap. Imagine a lone forager in Shark Bay wearing a sponge mask, prying into the sand for hidden meals. Imagine a calf learning to surf its first wave, stumbling in currents while its elders arc beside it like silver scythes. Each of these scenes speaks not just to instinct but to thought, to the passing of strategies through memory, to the refinement of skills through play. In the reef, mantis shrimp crack with thunder, jellyfish sting with lightning, cuttlefish dazzle with illusions, and octopuses plot with arms. Dolphins, by contrast, shape the sea through invisible architecture, sculpting bubbles into walls, weaving clicks into images, and turning water itself into a canvas of sound. They are predators, yes, but also engineers, teachers, and artists of the medium that defines them. Their mastery is not brute force, but the reprogramming of physics to serve their will. For humans who encounter them, dolphins inspire admiration, envy, and perhaps a measure of humility. To share the sea with an animal that builds traps out of air and reads the world in echoes is to confront intelligence not mirrored in our image, but alive in its own form. Their lives remind us that sound is not only communication, but architecture, that bubbles are not only play, but tools, and that culture can thrive even where hands cannot build. The polar sea is glassy with silence, broken only by the whisper of wind across ice. A lone seal rests on a floe, nose tucked into its body to conserve warmth, eyes closing against the glare of the sun. To human eyes, the floe seems safe, a frozen island adrift on a sea too wide for threats to approach unnoticed. But below the surface, in the cold blue expanse, a formation is building. Black and white bodies slice silently through the water in parallel lines, flanking one another with military precision. They are orcas, apex predators of the sea, preparing to turn physics into a weapon. What follows is one of the most extraordinary spectacles in the natural world, the wave wash hunt. The pod aligns in a row, each individual carefully positioned, each tail beat synchronized. They surge forward as one, their collective momentum pushing a rolling wave ahead of them. The swell races across the sea, lifts the edge of the floe, and tilts it into instability. The seal, startled, scrambles for balance. A second pass comes, stronger. The floe buckles, water sloshes over its surface, and the seal is swept into the ocean. In an instant, the orcas seize their prize. What makes this so remarkable is not just the outcome, but the orchestration. Timing must be precise. Each body must add power at exactly the right moment. Energy is not wasted but compounded as the group converts hydrodynamics into strategy. Few predators wield the laws of physics with such mastery. Orcas do not confine their ingenuity to ice. In warmer waters, they exploit other principles, tailoring techniques to prey and terrain. When hunting sharks, they employ a tactic both brutal and surgical, rudder biting. By targeting the tail fins, orcas disable their quarry's propulsion, exhausting it until resistance wanes. Then comes a maneuver that reflects learned expertise, flipping the shark upside down. In this inverted state, many sharks enter tonic immobility, a trance-like paralysis where muscles lock and senses dull. An orca can hold a shark in this state for minutes, long enough to strip its liver, a rich, oily organ dense with energy, before leaving the carcass adrift. This behavior is not instinctual. It is transmitted knowledge, passed from experienced hunters to younger pod members. It is predation elevated to craft, where anatomical weaknesses are exploited with deliberate precision. The coordination behind these hunts is made possible by communication as complex as it is subtle. Orcas live in matrilineal societies, where knowledge flows through generations under the guidance of mothers and grandmothers. Within these family groups, individuals produce calls, clicks, whistles, pulsed sequences that form distinct dialects. To a hydrophone, these calls are easily distinguished between pods, much like human languages. One group's repertoire may include rising whoops and descending squeals, another's may feature rapid staccato bursts. The dialect is more than a signature. It encodes identity, bonds individuals, and structures cooperation. Calves learn their pod's language as they learn its hunting techniques, absorbing culture as much as biology. Culture, in fact, shapes the orca's diet as profoundly as climate shapes its range. Around the world, ecotypes of orcas exist, each with specialized prey and strategies. In the North Pacific, resident pods focus almost exclusively on salmon, honing techniques to intercept migrating schools. Offshore groups, by contrast, target sharks, their teeth worn down by the abrasion of cartilaginous skin. Transient orcas pursue marine mammals, hunting seals, sea lions, even whales, often in stealthy silence to avoid alarming their quarry. Move to Antarctic waters, and a different picture emerges, pods that coordinate wave-wash hunts against seals or pursue minke whales across expanses of ice. In New Zealand, some orcas feed primarily on rays, flipping them belly up to disable them before consumption. These differences are not genetic divides but cultural ones, passed through social learning, reinforced by tradition, and adapted to local ecosystems. Orcas are global, yet each pod is provincial, shaped by knowledge inherited across generations. Such sophistication carries implications far beyond the thrill of predation. When orcas target seals on ice, they alter the survival patterns of those populations, pressuring them to adapt to shifting ice conditions. When pods specialize in salmon, their fortunes rise and fall with fisheries, tying their fate to human exploitation. In some regions, the depletion of key prey has led to declines in orca numbers, a reminder that even apex predators are not insulated from the ripples of ecological change. Their brilliance as hunters makes them formidable, but their reliance on culture makes them vulnerable to disruption. Remove salmon, and the salmon hunting pods suffer disproportionately. Reduce ice, and the physics squads of Antarctica lose their stage. The ethical questions their behavior raises linger in human minds. When a pod isolates a grey whale calf, surrounding it for hours until exhaustion sets in, the spectacle evokes both awe and discomfort. These are not mindless attacks but prolonged sieges, coordinated with eerie precision. The mother's futile defense, the calf's final breaths, and the orca's efficient consumption reveal intelligence not dulled by empathy. Yet to condemn orcas as cruel is to impose human morality on an evolutionary process that values survival above sentiment. To revere them as noble hunters risks overlooking the ecological consequences of their efficiency. Orcas remind us that apex intelligence, when combined with apex predation, reshapes ecosystems in profound ways. They are both marvel and menace, architects of balance and harbingers of decline. Still, the awe they inspire is undeniable. Picture the Antarctic scene again. Ice floes fractured into shards, the sea alive with black fins cutting the surface, each rise and fall a note in a choreography older than memory. These predators are not improvising. They are executing a script honed over generations, a physics experiment repeated until it became instinct, passed down not in genes, but in stories of sound. To witness it is to glimpse intelligence applied not to tools or cities, but to waves and ice, the raw elements of the sea itself. The orca stands as one of evolution's most ambitious experiments, a predator that is not only fast, strong and social, but also cultural, inventive and adaptable. Its black and white body has become a symbol of the wild sea, but its mind is the true wonder. It carries traditions in its calls, manipulates hydrodynamics with its hunts, and binds families through the memory of shared strategies. Its presence in any ocean is both a guarantee of ecological drama and a warning of fragility. For when the architects of physics begin to falter, it is not just their survival that is at stake, but the balance of the oceans themselves. Night falls across the tropics, and with it comes a shift in the rhythm of the sea. The reef fish retreat into crevices, the day's bright chorus giving way to a subtler murmur. Moonlight lays a silver sheen over the water's surface, a world of silhouettes and shadows, faint ripples spreading across a vast and restless plain. From below a shape rises, thick-bodied and slow, stripes faintly visible across its flanks. It is the tiger shark, part scavenger, part sprinter, a predator equipped not with speed alone, but with an extraordinary suite of sensory tools that make the ocean an open book of opportunity. The first of these tools is hidden within its broad snout. Scattered across the shark's head are thousands of tiny pores known as the ampullae of Lorenzini. Each pore leads to a jelly-filled canal connected to specialized cells capable of detecting the faintest electrical signals. Every living creature generates bioelectric fields through muscle contractions and nerve impulses. For most predators, these signals are imperceptible, drowned in the sea's complexity. For the tiger shark, they glow like a beacon. A buried fish, invisible beneath sand, betrays itself with the twitch of its gills. A resting turtle, still and camouflaged, cannot hide the gentle hum of its heartbeat. Even seabirds that drift exhausted on the surface emit electrical signatures through their muscles, allowing the shark to locate them under cover of darkness. This sensory layer gives the tiger shark the ability to hunt in dimensions unavailable to most predators, turning the ocean into a living electrical map. But its range extends far beyond close-quarters detection. The tiger shark is also guided by one of the most acute olfactory systems in the sea. Along channels in its snout, water passes continuously over folded tissues studded with chemoreceptors. These receptors can detect trace molecules at astonishingly low concentrations, allowing the shark to follow chemical trails across kilometers of open water. The scent of a whale carcass, drifting outward in a slow ribbon, becomes a summons that may draw scavengers from miles away. The shark does not swim blindly. It rides currents, sampling and resampling the flow, angling its body until the gradient sharpens, following the invisible thread back to its source. It is this ability that makes tiger sharks among the ocean's foremost janitors, arriving at carcasses long before decay sets in, recycling nutrients and preventing rot from lingering in the ecosystem. Magnetonavigation provides yet another dimension of awareness. Embedded within their tissues are iron-rich particles sensitive to Earth's magnetic field. Evidence suggests tiger sharks, like many migratory species, use geomagnetic cues to orient across vast stretches of ocean. Their movements are not random but purposeful, tracing lines invisible to us, pathways that link feeding grounds, pupping areas, and migratory corridors. This internal compass allows them to traverse open seas with uncanny accuracy, an essential adaptation for a predator that does not specialize in one habitat, but roams from shallow reefs to pelagic blue waters. At night, when the sensory advantages of electroreception and olfaction are heightened, tiger sharks often turn their attention to turtles. Green turtles, loggerheads, and hawksbills rest at the surface or along sandy bottoms, vulnerable as they rise to breathe. From below, the shark ascends with steady, unhurried power, guided by the outline of the turtle's silhouette against the moonlit surface.
The strike is sudden, a surge upward, jaws spreading to reveal serrated teeth designed not for delicate precision, but for sawing through thick shell and bone.
Unlike great whites, which rely on momentum-driven ambushes, tiger sharks are opportunistic sprinters. They accelerate in short, decisive bursts, overwhelming prey before it can react. For turtles whose evolutionary armor has shielded them from most predators, the tiger shark remains a rare and formidable threat. The same tactics extend to seabirds. Storms often drive fledglings from nesting islands into the ocean, where they struggle, waterlogged and exhausted. To a tiger shark cruising near the surface, the bird's silhouette is unmistakable. Studies of stomach contents have revealed a surprising number of feathers alongside the remains of fish, turtles, and squid. This opportunism underscores the shark's strategy. It is not bound to one niche, but takes advantage of whatever the sea offers. Perhaps the best window into its role as an ecological opportunist lies in the peculiar inventory of its stomach. Biologists examining tiger sharks have found not only expected prey, fish, rays, sea snakes, dolphins, but also less obvious items, license plates, tires, even chunks of coal. While the media often sensationalize these garbage gut discoveries, the truth is more nuanced. These objects are not evidence of indiscriminate gluttony, but of an evolutionary strategy tuned toward survival. Tiger sharks test objects in their environment, biting first, evaluating later. Their broad, serrated teeth and robust jaws allow them to process tough, unyielding matter, so even if the item proves inedible, the exploratory bite costs little. More often than not, these tests are directed at legitimate prey, armored turtles, dense rays, or whale carcass bones. The occasional non-food object is the byproduct of curiosity in a changing ocean, one increasingly littered with human debris. By consuming such a wide variety of prey, tiger sharks exert a stabilizing influence on marine ecosystems. They reduce turtle numbers, preventing overgrazing of seagrass meadows, which in turn shelter fish and absorb carbon. They scavenge carcasses, recycling nutrients back into the food web and limiting disease risks. They target weak or injured individuals, culling populations in ways that maintain genetic strength. In this sense, tiger sharks embody the paradox of apex predators, feared as killers, yet indispensable as regulators of life beneath the waves. And yet the relationship between tiger sharks and humans is layered with tension. In tropical waters where swimmers and surfers enter the sea, encounters occasionally end in bites. The tiger shark's reputation as dangerous is not undeserved, but it is also disproportionate. Attacks are rare compared to the millions of people who enter shark habitats each year. Most incidents stem not from deliberate predation, but from investigative bites, tests that for humans can have serious consequences due to the shark's size and power. Far more often, tiger sharks avoid humans entirely, ghosting past divers without incident, uninterested in flesh that does not match their evolutionary history of prey. What is certain is their importance. To remove tiger sharks from reefs would be to unravel unseen threads. Turtles would overpopulate, seagrass beds would thin, and the cascade would reach into fisheries and coral dynamics. Carrion would linger, altering bacterial communities and nutrient flows. The ocean would grow less efficient, less resilient. It is a reminder that predators, however frightening, are often the architects of balance. To watch a tiger shark in its element is to witness the sea as an interwoven field of senses. It glides with casual authority, but every pore, every receptor, every beat of its tail is tuned to a complex network of signals. The faint electrical flicker of a hidden fish, the chemical ribbon of distant carrion, the magnetic pull of a migratory corridor, the silhouette of a turtle at the surface, breathing under the moon. It is a predator designed not merely for attack, but for interpretation, a living sensor array moving through the ocean's endless darkness. Where mantis shrimp crack with force and orcas coordinate with strategy, the tiger shark rules with perception. Its power lies in knowing more than its prey, in seeing the unseen, in hearing the unspoken hum of life itself. For the ecosystems it patrols, it is both scavenger and sentinel, both hunter and janitor. For us, it is a reminder that the ocean's fiercest guardians are not villains, but keystones, holding together worlds that would collapse without them. The reef at night transforms into a world of shadows and hidden currents. By day it is a carnival of color, parrotfish rasping coral, angelfish gliding past sponges, sunbeams fractured into rainbows by swaying water. But when darkness falls, the palette drains. Only the faint glow of bioluminescent plankton and the sweeping cones of moonlight remain. It is in this realm, where sight is muted and smell takes precedence, that the moray eel becomes the reef's silent enforcer. From the crack of a coral head, a snout protrudes, its skin patterned with mottled greens and browns, eyes scanning with patient stillness. The mouth gapes rhythmically, not in aggression but in necessity, for the moray breathes by pumping water over its gills. The effect, however, is unsettling. To a diver's light, the creature appears as a set of jaws hovering in darkness, teeth glinting, body concealed within the labyrinth. What makes the moray more extraordinary than its eerie appearance, however, is hidden deep within its throat, a set of secondary jaws unlike anything else in the animal kingdom. These pharyngeal jaws are the moray's evolutionary trump card. Where most fish rely on suction to pull prey into their mouths, morays face a problem. Their elongated, narrow skulls lack the mechanics for strong suction. The solution is a structure that seems almost alien in design. Behind the primary jaws lies a second set, hinged and muscular, armed with teeth of their own. When the moray strikes, it seizes prey with the outer jaws. Then the inner pharyngeal jaws shoot forward, latching onto the struggling fish or crab and hauling it back into the throat. The sequence unfolds in fractions of a second, a two-step capture that ensures no victim escapes once contact is made. To witnesses, it recalls science fiction nightmares, the reef's own xenomorph, with jaws within jaws. This mechanism is more than a curiosity. It is a necessity born from the moray's hunting style. The eel is not a pursuer like a barracuda, nor a sprinter like a shark. It is an ambush specialist, relying on confined quarters and sudden bursts of violence. By night it patrols the labyrinth of coral crevices and rocky fissures, its long, muscular body perfectly adapted for tight turns and narrow passages. Unlike fish with rigid skeletons, the moray's skull and vertebrae are loosely connected, allowing it to bend and coil with serpentine agility. Where other predators cannot follow, the moray can. The eel's hunting begins with its nose. Lacking the keen eyesight of many reef predators, morays rely heavily on chemoreception. The inner linings of their nostrils, known as nares, are studded with sensory tissues that detect chemical traces in the water. A faint plume from a hiding damselfish or the lingering scent of a wounded parrotfish is enough to guide the eel. Moving with deliberate patience, it threads through coral alleys, its tongue flicking against the water to test the chemical trail. Then, without warning, the stillness erupts into motion. The eel lunges, jaws flashing forward, and within moments the prey is dragged back into darkness, pulled deeper by the alien grip of the pharyngeal jaws. Morays do not hunt alone. In some regions, they engage in one of the most remarkable examples of cross-species cooperation in the ocean, the moray-grouper alliance. Groupers, broad-bodied hunters of the reef, lack the ability to probe tight crevices where prey often retreats. Morays, in contrast, are masters of these labyrinths but less efficient in open chases. Together they form a hunting duo greater than the sum of its parts. A grouper seeking assistance performs a headshake signal near a moray's lair. If the moray responds, the two set out side by side. When prey darts into cracks, the moray slithers in, flushing fish into open water where the grouper waits. If the prey bolts too far, the grouper blocks exits, steering it back toward the eel. In some cases, both predators benefit directly, sharing in the catch. This cooperation is not fleeting chance, but deliberate coordination, evidence of intelligence and behavioral flexibility in both species. To see two predators from entirely different lineages work in synchrony is to witness evolution's pragmatism. When competition gives way to collaboration, survival prospers. The moray's body itself is tailored for its chosen role. Unlike many fish, which rely on scales for protection, morays are wrapped in a thick coat of mucus. This slippery film reduces friction as they slide through rough coral, protecting skin from abrasions. The mucus also contains antimicrobial properties, shielding wounds from infection in an environment where parasites and pathogens thrive. Their elongated finless form, lacking the pectoral and pelvic fins of most fish, grants them unmatched maneuverability in mazes of stone. Every coil, every flex of muscle is a negotiation with space, a dance of compression and release that allows them to twist into places no other predator can reach. Such specialization carries ecological consequences. By preying on small fish, crustaceans, and cephalopods hidden within the reef, morays exert control over populations that might otherwise boom unchecked. Without morays, certain damselfish or wrasse species could dominate, altering algae growth and coral dynamics. The eel, often unseen, thus plays a keystone role, not the most visible hunter, but one whose influence radiates through the reef's balance. In ecosystems already stressed by warming waters, bleaching events, and human interference, the loss of morays would ripple outward in unpredictable ways. Their role as regulators is sharpened by their nocturnal rhythm. By hunting at night, morays complement the daytime predation of diurnal hunters like snappers and groupers. Together, these overlapping schedules create a near-constant pressure on prey populations, ensuring that no time of day offers complete safety. This temporal partitioning demonstrates the elegance of ecological balance, different predators sharing the reef, not through truce but through timing, carving niches that together stabilize the whole. For humans, encounters with moray eels inspire a mixture of fascination and fear. Their habit of opening and closing their mouths, necessary for breathing, is often misread as aggression. Divers peering too close into a lair may receive a defensive snap, and bites can be serious, given the eel's sharp teeth and powerful jaws. Yet morays are not reckless attackers. They prefer retreat to confrontation, their energy reserved for hunting rather than defending against intruders. Most injuries result from provocation or misguided feeding attempts. In truth, the moray eel is no more malevolent than any other predator. Its strangeness lies in its adaptations, not in malice. Seen through the lens of evolution, the moray eel is both specialist and innovator. Its pharyngeal jaws solve a problem of skull design by creating a system more terrifyingly effective than suction alone. Its cooperative hunts with groupers demonstrate that intelligence in the reef is not the sole domain of dolphins or octopuses, but arises wherever opportunity demands. Its mucus-coated body and labyrinthine agility mark it as an architect of hidden spaces, a predator of shadows who shapes the reef from within. To drift over a coral head at night and glimpse a moray eel's face protruding from the dark is to feel the reef watching back. The steady gape of its mouth, the glint of its teeth, the knowledge that within lies another set of jaws, these impressions linger. Yet beyond the fear lies respect. The moray eel, with its alien physiology and understated role, is not simply the reef's monster. It is the reef's balance keeper, a silent hunter that ensures no crevice becomes too crowded, no prey too dominant. In a world where mantis shrimp break physics, cuttlefish edit their skin, and dolphins sculpt bubbles, the moray eel carves its legacy in shadows. It is the predator of labyrinths, the master of jaws within jaws, an animal that shows how strangeness can become necessity and how the hidden can govern the whole.